Okay, welcome back to the second notebook. It's called Deep Learning with PyTorch, and we first discussed some basic ideas of deep learning, which we will not go into detail because they should already be part of your machine learning course. But just to, as a reminder, and to see how it works in PyTorch. So the first thing is called affine maps. It's the basic operation in a neural network where you have an input layer, you multiply the inputs by some weights which connect the input to the output, and as a result of this operation you have the outputs. This operation is here represented as a function on the inputs, which is the inputs are x, it's usually a vector. You multiply this vector by the weight matrix, you add a bias term, and you get the output of this function, the outputs of this function. Yeah, please read again the description. How is this done in PyTorch? Here we define some input, two rows, each has 5 values in it. So the input has 5 values. We have 2 training examples. This is our input data. And then we define the mapping from the input to the output. Here as a linear layer. And to compute the outputs, we just apply this linear layer to the input data, which gives us some result. The main thing which we have to consider here is the dimensionality of the inputs and the outputs. So if you know that, for example, your input has like a word embedding 300 dimensions, and you want to have one output layer, an output layer with, let's say, 10 elements in the output layer, then you have to define this linear layer with 300,5. Then you have this mapping from 300 to inputs to 5 outputs. So here we have 5 inputs and 3 outputs. So this dimensionality here, it's important for, so that the shapes of the tensors match. Okay, so this was the basic linear operation, the matrix multiplication. To be able to represent more complex functions in deep learning, we need to add non-linearities to our architecture of the network. There are 3 main non-linearities used, which is tanh, sigmoid, and ReLU. For us now it doesn't really matter to understand or to know which one to use. Nowadays often tanh or ReLU is used in practical applications. So what do those non-linearities do? They just add some non-linear operation to our network. Because if we would have only linear operations in the network, then it would basically just be one big matrix multiplied to the inputs. So we could not really represent complex functions and complex operations in our neural network. Okay, please again read this description of non-linearities. How to apply them. It's very simple. So here we have some data defined. This could be the output of the previous operation. So we have some data vector, or some matrix in this case, and we want to apply a non-linearity to this data, and we just do it in this way. So the ReLU non-linearity, it's in this functional interface package, whatever it is, and we apply this to our data. And what the ReLU does, it just makes negative numbers, it just sets them to 0. So as you can see here, you have an input tensor with some negative numbers, and the negative numbers are set to 0. So very simple non-linear function applied. Next thing is softmax, which is usually used as the last layer of your or it's applied to the last layer of your network, and it creates a probability distribution where the sum of all of the probabilities is 1, which is basically the definition of a probability distribution. So let's have a look at some example again. So here we have some data. It's a vector of 5 random numbers, and we say that this is the final result of our network operations. And then what we want is a probability over the classes which we're trying to predict. So we transform this 5 numbers into probabilities. So if you look at the output of this operation, so here we have these 5 numbers which the network generated, and these are then transformed into probabilities which add up to 1. So if we classify, is this document about sport or is it about politics, then we get probabilities, and we can choose usually the class with the highest probability. And as you can see, there is obviously a connection between the initial values and the probabilities. So where the initial value was really low, -1.3, the probability is very low, and where the value was the highest, then also the probability is the highest.